Hello and Happy New Year to everyone, let's hope. Welcome to the January 2021 Recreational Astronomy Night Meeting online edition of the Royal Astronomical Society of Canada, Toronto Centre. My name is Paul Markov, and aside from introducing the speakers, I also search for presentations for upcoming meetings. So if you have a presentation in mind, please get in touch with me. We have openings for the March and later meetings. Now, because we're no longer tied to the Ontario Science Centre schedule, our meetings are going to be on the first Wednesday of each month going forward, at least until we get to go back to the Science Centre for our meetings. Before we start the presentations, I would like to thank in advance our technical team comprised of Andrew and Betty Reed, Blake Nancaro, Ward Legros, and Daniel Ciulucci. Thank you for making these online presentations possible. We have three speakers this evening, and I expect that the meeting will be done around 9:30 as usual. The speakers are Chris Vaughan with The Sky This Month, Bryon Czarnik will talk to us about football and astronomy, the making of the Great Magellan Telescope mirrors. And then Tom Otvos will give us an update on making a thin meniscus telescope mirror. And finally, Tom Luton, our president, will close off the meeting with the usual announcements. So if you have a question for our speakers, please enter them in the YouTube chat box, and Blake will ask the speaker on your behalf. But also, if you are attending a meeting for the first time, whether you're a member or not, please just say hello and introduce yourself in the chat box. I think we're ready to go, so let's get started tonight's meeting with Chris Vaughan and The Sky This Month. Go ahead, Chris.
Thanks, Paul, and hello, everybody. So tonight I'm going to cover what's going on in the night sky between tonight and the first Tuesday of February, which is the day before our next RASC, Recreational Astronomy Night meeting. You might enjoy this nice background slide I've had here. This is a deep, long exposure photograph of the southern half of the constellation Auriga, the Charioteer, and this is a sampling of some of the nebulas and open clusters that are hidden treasures inside that constellation. So I recommend checking that out. So what I'm going to cover is a bit on space exploration news, launches, things like that. I'll review some events in history during January, and then we'll get into observing things to do with the sun and the moon, the planets, comets, asteroids, satellite passes, and then some observing suggestions for variable stars, doubles, and winter targets, etc. And following the presentation, I'll upload the notes for this meeting, this presentation, to our website, rascto.ca. So in case you're feeling that you want just the bullet point headlines of what I'm going to talk about in more depth, here's a sort of bullet point list of some of the milestone events covering the next few weeks. So right now we're entering a dark sky moonless viewing period, so that's great. We have long nights to use those with. On January 10th in the evening, we've got the variable star Algol brightening from its minimum. On the 10th, that's Sunday, we have a really close meetup of Jupiter, Saturn, and Mercury low over the western horizon after sunset. And then on the 16th, the moon will be turning to make its eastern limb more favorable for us to view some of the features on the edge of the moon. On the 20th of January, we've got Mars doing a close flyby of Uranus. They'll be telescope close. On the 21st, I'm going to suggest you take a look at the lunar straight wall. We've got an asteroidal occultation on the 22nd, and then to finish the month, last week of the month, we've got Mercury at max visibility and maximum elongation. In space exploration, not too much going on in launches right now, except for there's a large number of to-be-announced Falcon 9 rockets launching more Starlink satellites and other small commercial CubeSats and microsats. But this other launch opportunity is one to look for. This is the Virgin Orbit Launcher 1 rocket, which is the little rocket you can see strapped to the undercarriage of Cosmic Girl, their Boeing 747 launching from the Mojave Air and Space Port in California. And they're launching CubeSats, for NASA field centers and some educational purposes and so on. But that's a neat, another way of commercial space exploration ramping up these days. Looking back in history, so on January 8th, 1942, we celebrate the birthday of Stephen Hawking, theoretical astrophysicist, author, TV personality. I guess he hoped to be an astronaut, but unfortunately we lost him in 2018. Then on January 10th, we celebrate Robert Woodrow Wilson. He co-discovered the cosmic microwave background radiation. Way back in 1642, on January 8th, we lost Galileo Galilei at age 78, but we celebrate the birth of Doctor Who in 1908, William Hartnell. 2014, someone that's near and dear to many of us in amateur astronomy, it's John Dobson. He lived to a ripe old age of 98. He's the one that developed the Dobsonian telescope that many of us use today. You can see a sort of an earlier, less refined version of a Dobsonian reflector there on the lower left. On January 16th, it's Jill Tarter's birthday, American SETI pioneer, search for extraterrestrial intelligence, and radio astronomer. And here she is sitting, I'm sure at one of her favorite places on the Arecibo radio telescope that we recently lost due to its collapse. Back in 1611, January 28th, Johannes Hevelius, what a man, Polish astronomer, lunar cartographer. He worked on libration. He built a 46-meter long focal length telescope, tubeless telescope. He discovered 4 comets. He named the star Mira, which I'm going to touch on later on. He identified a number of modern constellations and more. Here's a picture of his telescope. And there's one of his moon maps. In space exploration, back in January 19th of 2006, the New Horizons mission launched. It's the one that flew past Pluto and then the Ultima Thule Kuiper Belt object. On January 25th, the Opportunity rover landed on Mars. January 27th, the sad anniversary of the loss of the Apollo 1 crew of Grissom, Chaffee, and White perishing in their capsule due to a fire during training. And then again, another sad anniversary for NASA is the shuttle Challenger exploding shortly after liftoff at the end of January. In astronomy this month, we celebrate Galileo turning his new spyglass to the heavens and beginning to observe the craters and mountains on the moon, seeing that there are spots on the sun, watching the moons revolve around Jupiter, and capturing the phases of Venus. Really started astronomy, visual astronomy for everyone. 1939, we have the Scottish astronomer Thomas Henderson publishing the first stellar parallax measurement. That's using the orbit of the Earth, the Earth's position changing due to its orbit around the sun causes the position of stars to be detectable, and we can calculate using trigonometry their distance. 1969, we have the discovery of the first optical pulsar in Messier 1, that's the Crab Nebula, by John Cook and Michael Disney using the 36-inch telescope at Kitt Peak Observatory. And on January 17th, we celebrate Edwin Hubble publishing his paper that declared that the universe is expanding. And there's the red line running through his data points, showing that expanded distance over velocity. In 1862, Alvin Clark, the Clarks were famous telescope makers, discovered Sirius B, the little white dwarf star that's tucked in close to the bright star Sirius. There's a little arrow next to the Sirius B. People call it the flea, the pup. I prefer calling it the flea. And on February 1st, the first light for the 200-inch Hale telescope at Mount Palomar, California. I don't know if you can notice, there's a whole crowd of people sitting underneath the telescope, just to give you a sense of scale. Let's get into some observing. This is a fantastic picture of the region near Alnitak. So Alnitak is this bright star. It's the left-hand star of Orion's belt. The rest of Orion's belt heads up to the right here. And this was taken by Michael Watson, one of our Toronto Centre members. And I just wanted to point out that we have the Horsehead Nebula here in this long exposure. We have the Flame Nebula tucked in close to the star. And then we have this little grouping here. This is Sigma Orionis. And this is one of the multiple star recommendations for viewing multiples this month. Rascals are invited to help with mapping light pollution through the globeatnight.org organization. So during the dark of the moon every month, They choose a constellation, and they ask you to estimate how many of that constellation stars that you can see visually from your location, and then log those readings into their database so that they can figure out how light pollution is distributed across the world, and also how it varies over time, how it's getting worse, normally getting worse. So this month, between now and the 13th of January, they're focused on the constellation of Orion. And you can get more details at www.globeatnight.org. Sunrise and sunset is important for astronomy. Right now, the sun is rising at about 7:50 in the morning and setting around 4:56 p.m. And that gives us 9 hours of daylight. But by the time we get to our next meeting, the amount of daylight will be increased to 9 hours and 58 minutes. So our nights are getting a little shorter, our days are getting longer. Here's a graph of the sort of the bright blue is the amount of daylight per day, and the dark is the amount of night per day. You can see that the wedge as the daylight lengthens with each passing day. Astronomical twilight is important to astronomy. When the sun is more than 18 degrees below the horizon, the sky is as dark as it's going to get, not counting the moon and other things, the light pollution and so on. So imagers that want a dark sky, they need to wait till the sun has gone well down and then finish their job, their imaging, before the sun starts to rise in the morning. Right now, the astronomical twilight, the full true darkness occurs after about 6:39 p.m. and the sky will begin to get light around 6:07 a.m. tomorrow morning. So that gives the imagers about 11.5 hours of imaging time, but that's decreasing by a minute and a quarter every day. 4 weeks from now, we'll be down to 10 hours and 45 minutes of imaging, and the days will be lengthening. Daylights will be lengthening, the nights will be shortening by 2.5 minutes per day. So here's a graphical overview of what the moon is up to this month, starting at tonight's meeting on the January 6th and then running to the February 2nd period that I'm covering here. So we see we're at the third quarter or last quarter moon tonight, and then the moon will wane towards new a week from now on the 13th, and then it'll reappear in the evening sky for first quarter, and the full moon will occur towards the end of January on the 28th. For those interested in dark sky viewing, we want to take a look at those dark skies between about now, at last quarter, third quarter, and within a day or two after new moon, when the moon begins to sort of linger in the western horizon after sunset. It goes down early, leaving the rest of the night nice and dark. So this is our dark sky viewing, best dark sky viewing period. Now, if you want to look at the moon itself, the best time to do that is when it's waxing in the evening, and that will be starting up around the 15th, 16th of the month and extending through that first quarter week, the week sort of surrounding first quarter. And while the moon is waxing, a number of topographic features on the moon become very, very nicely positioned and enhanced for our viewing, including things like the lunar straight wall, the golden handle. And as the moon gets towards full, we can look for a feature October. Let's get my audio back here. Because COVID-19 is keeping more of us near home, we're not able to necessarily go out to our dark sky sites. I'm encouraging people to spend time looking at the moon. So the moon is going to be visible in our evening sky for most of the rest of this month, all the way to February 2nd or so. In the winter, the moon is higher in the sky, so we're getting sharper views of it through less of the atmosphere. Don't forget, you can view the moon in the morning daytime too. So get the telescope out, cooling down overnight, pull it out in the morning. And you can use a polarized filter. You could take you can get a polarized filter for the moon, or you could just take a pair of 3D glasses from the cinema and rotate the glasses through 360 degrees, and you can darken the sky and enhance the contrast on the moon in the daytime. So that's a neat trick. Now the moon does this wobbling and nodding through the course of the month. That's because its orbital inclination is tilted 5 degrees to the ecliptic, and because it has an elliptical orbit around the Earth. And that means that that the center of the moon rises and falls and drifts left and right through the lunar month. That's called libration. And over time, we can see about 59% of the moon's Earth-facing hemisphere. So the Observer's Handbook of the RASC lists for each month the times when the moon is most tilted left to east to west to north to south. And I've got some suggestions here. So on the 16th of January, the moon's eastern limb, that's the side that it's filling with light from during the sort of post-new moon period. From the northern hemisphere, if you're looking at the moon, the eastern hemisphere of the moon would be on the right-hand side from a viewer standing in the northern hemisphere. So on the 16th, the moon will be tilted so that we can see more around the corner on the eastern side. And you can look for things that are normally elusive, things like Mare Smithii, Mare Marginis, and the crater Hubble. The librations for the northern limb happens in darkness. That's not helpful. The moon's western limb is exposed when the moon's full. That's not as helpful either. And when the moon's southern limb is most exposed, it's going to be rising in late evening. And there are a few features listed here that you can attempt to see during those favorable librations. So here's just a quick example, a picture taken when the moon is not librated favorably on the east and then when it is. And so this would be an example of being able to see this dark smudge of Mare Smithii in the sort of northeastern quadrant of the moon's disk. A few days later, when the moon is getting towards past first quarter, so a day or two past first quarter, we can favorably see this lunar straight wall, otherwise known as the Rupus Recta. It's 110 kilometers long. It's sort of runs across Mare Nubium. And Mare Nubium is the dark patch, the dark mare that sits just above the crater Tycho. When you're looking with your binoculars, you should be able to pick that out. Good binoculars might see the straight wall. Certainly any size of a telescope will be able to see it. And that feature is illuminated from the right a few days after first quarter, and then a few days before third quarter, it's illuminated from the left. So it gets a bit of a different view. The golden handle effect is produced when the former rim of a crater named that's now known as Sinus Iridum, or the Bay of Rainbows, it sits on the edge of Mare Imbrium, and part of the crater has been submerged under the basalts that flooded Mare Imbrium, leaving just a half of it exposed. And a few days before the full moon, the shallow sun angle lights up the eastern side of that curved wall. We call these the Jura Mountains. And where the crater edges dive into the Mare Imbrium, we get these little points, promontories. This is Heraclides and Laplace. And so the effect produces kind of a teacup handle shape on the edge of Mare Imbrium we call it the lunar handle. Once you've got it, you can certainly see this with unaided eyes and binoculars and telescopes, but then grab your telescope, zoom in and see if you can see the dorsi. Those are wrinkle ridges that kind of run north-south through Mare Iridium. Now here's a cool resource that a number of us are using lately. It's called the NASA Dial-A-Moon. So you can go to this website, and this has, for every day of the year, 2021, and for every hour of that day, a picture of the moon properly illuminated as you would see it from Earth. And so what you can do is you can dial up using universal time, the date and time, and it'll show you a picture of the moon. Then you can click on that picture and it'll download to your computer a TIFF file, a very large TIFF file, many megabytes in size, with a high resolution annotated view of the same moon. And you can get a version that's right way up or upside down if you wanted to use it at the eyepiece for a telescope. This is a great way to confirm when the lunar X is scheduled to appear. You can see the lunar X hour by hour and declining when it's done. So it's a great resource. As the moon gets towards full later this month, around the 26th to the 30th, that's when we're starting to see the lights and dark patches on the moon are more caused by the moon's geology as opposed to by its topography and by shadow effects. And so what you can look for towards the full moon period are these ray systems emanating from some of the craters. That's the ejecta that was blasted out of the craters and strewn across the moon's surface. There are ejector craters around Tycho and Copernicus. There's a neat one named Proclus, which is an ejecta pattern that's not 360 degrees, but it's only about 2/3 of a circle because the object that made it came in at an angle. And speaking of that, there's another one called Messier, and it's called Messier. The craters are called Messier because the rays produced by the object that hit was coming in at such a low angle that the debris was spread in only one direction, producing this sort of appearance of a comet through your telescope when you're looking at the moon. The Messier pattern is sitting here in Mare Fecunditas, and it's on the right-hand side of the moon's near-facing disk. Another thing that's cool near a full moon is to look for the terracing around the crater Copernicus. Here's the detailed view of it. You can see these sort of flat steps down the edge of the moon, down the edge of the crater, where the material at the edge of the crater has slumped and produced these little cliffs. Those are terraces. You can also look for these dark haloed craters. You can see there's a little crater here that's been punched through and a dark ring around it. And that's because the object that came in later than Copernicus has punched through and has excavated the dark material that is underneath the ejecta blanket of Copernicus. So when the moon is near its full phase, it's opposite the sun in the sky, and that means that all of the light landing on the moon is coming in at a very steep angle. And when that happens, it accentuates features like the terraces surrounding the crater Copernicus. This is the large crater in the upper sort of central western half of the moon's near-facing hemisphere. And so here's a magnified view of this sort of cliff edges you can see all the way around the surface of the edge of the crater due to the material slumping inside the crater, so these terrace effects. Another thing to look for are the little craters with dark halos around them. So in the area around Copernicus, we have the dark gray basalt underneath, and then we have the brighter material that was ejected when Copernicus was formed, forming a skin of white rocks sort of strewn on top of that. And then if an impactor comes in later, punches a hole in that, it excavates down into the dark basalt and spreads its little ring of ejecta on top of the Copernicus, the bright Copernicus ejecta. So we get, instead of having the normal effect of a crater with a white ring around it, we have craters that have little dark rings around them. And there are a whole bunch of them inside the ejecta blanket surrounding Copernicus. That's a terrific thing to look for in a telescope. You can also, at the full moon, look for the dark stains left by now dormant volcanoes on the moon. And so one of the best places to look for that is just below the center of the moon's disk, the crater Alphonsus. And here's a picture by Gary Czarnik of the Alphonsus crater. And you can see these three dark stains in a triangle. And these are former cinder cones of volcanoes that have since gone dormant, but were active at some point in the past on the moon. Another pair of them can be seen up here in the crater Atlas. The crater Atlas is sitting up here towards the upper northeastern vicinity of the moon's disk. So those are some neat things you can look for, especially in a telescope. The Alphonsus dark stains are quite prominent, so you don't need a big telescope to see those at all. All right, let's move into the planets. So we're actually entering a period now where we're going to be losing most of the planets. We still have Mars up in the sky, but it's not as prominent as it once was. But just before we lose Jupiter and Saturn after their terrific great conjunction a week or two ago, we have them still sitting low over the western horizon after sunset. But what's happening over the next few days is that the little speedy planet Mercury is going to be climbing up to join them. So between about the 9th and the 12th of January, Mercury will be climbing up, passing Jupiter and Saturn. Jupiter will be more visible because it's brighter than Saturn is. But if you grab your binoculars after the sun is safely set, you can take a look for them. So this is Sunday. I'm showing you the view on Sunday evening, January 10th, when they'll form a neat little triangle about 2 or 3 degrees separate from each other. So this big circle here would represent binoculars field of view. And this arc I'm showing through Mercury is showing its orbital path. So it's going to be every night climbing up a little bit. So the night after the 10th, Mercury will be a little higher and so on. And then on the 14th, just several days later, we're going to have Mercury sitting about here, and then we'll have a young crescent moon forming a neat little line of the moon, Mercury, Jupiter, and Saturn. Just after sunset, you've got to be fast before they get too low in the west. Speaking of Jupiter and Saturn, they're gone into the sun and solar conjunction, passing solar conjunction on the 24th and the 29th of January, respectively, and they'll re-enter the eastern pre-dawn sky later this year in a month or two. That vision of Mercury, that appearance of Mercury will last all through the month of January and into early February. So it's a great time for us in the Northern Hemisphere to see Mercury. Not so lucky for people in the Southern Hemisphere. The geometry works differently and they don't get as good of a view as we will. Mercury will reach the tip of its orbit out here called Eastern Elongation on January 23rd. And it'll be best visible over a good window, 5:30 to 6:30 p.m. in the southwestern sky. If you use a telescope on Mercury, you're going to notice that the disk is nearly fully illuminated and that the disk size itself will grow in size quite a bit from 5 arc seconds to 9 arc seconds over the next 4 weeks. Venus has been up in the pre-dawn sky for months and months, but we're losing it now. It's swinging back towards the sun. By early February, it'll be all but gone, impossible to see anymore. But in the meantime, it's shining at a very bright magnitude 3.9. If you put your telescope on it, you're going to see, again, a not quite full disk. It's a waxing, nearly full phase. Its disk size is much bigger than Mercury's. It's about 10 arc seconds. And when you're up early, you want to take a look, see if you can see Antares shining off to the west, the star Antares. And on the 11th of January, we've got the old crescent moon sitting just about 5 degrees to the right of Venus in the pre-dawn sky. And this is your binoculars field of view for reference. As I said, Mars is still nicely placed for viewing in the evening sky. It's nice and high. After sunset, it's already quite near its highest point around 7 p.m. in the evening. A month from now, that'll be happening about 6 p.m. So we're starting to get Mars more into the western sky and not quite as high as it is now. But it's much dimmer and much smaller in a telescope than it was during opposition in October. It's already about, I think, about a tenth as bright and quite a bit smaller. But Mars is speeding along the ecliptic. And on the 20th of January, it's going to make a very close pass with the blue-green planet Uranus. And this circle I'm showing here is a 2-degree field of view. So they're pretty much telescope close if you use a low-power eyepiece, low magnification eyepiece. And then you can catch the blue-green planet, dimmer planet, with the bright reddish planet in the same field of view. Beware, though, that Mars will be about 160 times brighter than Uranus. So that same night, when they're closest, we've got a first quarter moon just below them in the sky. It doesn't do Uranus any favors, but if you're using your telescope, finding Uranus with Mars's assistance, then you should have no trouble seeing it. Mars is just going to keep getting dimmer and smaller as Earth continues to pull away from it. It'll be lingering in the sky for a number of months, but it's just not the fine target that it once was. Neptune is also available in the evening sky. It's a little bit lower than Mars and Uranus are, so we have less of a window to look at it. It's sort of an early evening target. It's in Aquarius. It's about a magnitude 7.9, which is certainly within range of any size telescope if you know where to find the planet. And what you can do is you can look for these set of quite prominent stars. They're not super bright stars, they're medium bright, but they're in the sort of knee of Aquarius here. We have Phi Aquarii, Psi, and Lambda, and they form a kind of just a little bit to their upper left of Phi, about 1 finger width or one degree. So you could try for that. And that distance between these two will actually increase a little bit over the next few weeks, but it'll still be in the same vicinity. Don't forget that the asteroid or dwarf planet Ceres is on the 23rd of January. Vesta will start a little bit of a retrograde loop. This path is showing it sort of turning direction and heading back the other way, which it'll do through its opposition in April, and then it'll finally finish this retrograde loop in late April. If you're interested in variable stars, Algol is one of the most accessible variable stars for beginner astronomies. It's an eclipsing binary system. That means there are 2 stars in the system, and one star passes in front of the main star and dims the total light output that we see. And that's because the orbit of the 2 stars is in the line of sight to Earth. So that means that we can see them, the one star passing across the other star. We can't see the stars doing it, but that's the effect, is to dim the light. So normally Algol, or Beta Persei, which is sitting here, it shines at a magnitude of 2.2, and that's comparable to this star Almach, which is at the end of Andromeda. But every 2.87 days, as the little star passes in front of the main star, the total brightness drops to magnitude 3.4 and back for over a period of about 10 hours. And the magnitude 3-point star is similar to this star right beside Algol, called Rho Persei. So by getting out and looking and see, does Algol look the same as Rho Persei? Does it look brighter? You can get a sense of where it's at in the cycle. Here's just a graphic of how the light output decreases when the 2 stars are lined up. So on Wednesday, January 20th at 8:53 p.m., that's the scene I'm showing here, Algol will be already at its minimum, so it'll be similar to Rho, and it'll start increasing over 5 hours. As it does that, it'll sink a little bit into the western sky. Or you can flip it around, and you can, knowing when it's going to be at minimum, you could start watching 5 hours ahead and watch it decrease. So on Sunday, January 17th at 7 p.m., it'll be at its regular brightness, but 5 hours later, it'll be down at the dim point at the magnitude 3.4. Another famous variable star is Mira, which is sitting here in the neck of Cetus, the sea monster. This is a view looking southeast at 7 o'clock tonight. So it's sitting right there in our evening sky. Here's Orion, just for reference, and Taurus. So this is a pulsating variable star. It's takes about 100 days to brighten up, and then it takes about 220 days to drop in brightness. So it does this periodically, cycle after cycle. And this is a graph of the brightness over time for the last 700 days. So we're sitting right here at now, and it's about magnitude 6.2. So it's right in the middle of its range right now, heading down. So it's something that you could keep an eye on, make a note of looking at now and again. Some other great double stars that we can talk about. So I mentioned that Sigma Orionis that was earlier in the picture that Michael Watson took. This is where it's located. It's about a finger's width to the lower right of Alnitak, the bright star in Orion's belt. It's a beautiful magnitude 4 star, a long dart-shaped multiple, 49 arc minutes in length. Here's another nice double Iota Cancri in Cancer. It's a blue and yellow pair, separated by 30 arc seconds. And then down here, this is a real showpiece. This is 145 Canis Majoris. Sometimes we call it the winter alberio. The alberio is a beautiful blue and orange or blue and yellow star that we look at in the summertime, and this is comparable. It's the same sort of idea. And don't worry about the fact that it's sitting quite low in the sky in this view. Canis Major rises as the evening goes on. So this is 9 p.m. In the next number of weeks, this will be getting higher and higher, and nicely positioned for viewing that double. A shout out to Blake Nancaro, who's been sharing every month suggestions for double stars to look at. And he's also organized an RESC double star observing program, which you can find here at this link. And I'm not going to talk through these in detail, but I'll just show the list, and people can grab a screen cap and note which these nice double stars to chase on the next clear night. Nice thing about double stars is the moon can be at any phase. They cut through the moon So you don't need to wait for a dark sky the way you would for a nebula or a galaxy. If you're chasing the International Space Station right now, it's showing up in the pre-dawn. That'll last until about January 10th. And then starting on the 16th, we'll be seeing the International Space Station in the evening sky between about 6 and 7:45 p.m. And here are a number of upcoming passes that if you want to make a note of. And you can use the website heavens-above.com and enter your location, and it'll give you a list of all the passes of the International Space Station for where you live. Lunar occultation or asteroidal occultation. So occasionally we get lucky and an asteroid in the solar system will pass in front of a star and dim that star's light. And that will allow us to actually measure the shape of that asteroid and tell us more information about the object. So here's an event that's happening not too far from the Toronto area. On January 22nd in the late evening at 11:28 p.m., an asteroid by the name of 333 Badenia, which is itself a magnitude 4.2, which is very dim, will occult a relatively easy to see star with this fancy name. The star brightness will dip by almost 4 magnitudes, which is quite dramatic, for 12.4 seconds. And it's located in the constellation of Taurus, which is nice and conveniently positioned in our sky. And the predicted path of the max occultation runs right through Hamilton and out through southwestern Ontario. But anybody located between the blue lines are in the error bars for the event. So if you're wanting to head down into Milton, Cambridge, KW, Woodstock area, even Niagara Falls, St. Catharines, you have a chance of catching that event. The more people that can observe the event and time it and can submit their information to the sites that do that are contributing to citizen science, because then they're helping us work out the actual shape of the asteroid. Here's a star chart or star field showing the actual star that will be dimmed. It's about a few degrees from Elnath, which is the upper star of Taurus's horn, the northerly horn tip of Taurus the bull. So it's in a conveniently placed neighborhood. We like to look at objects when they're highest in the sky, because that way we're looking through the least amount of atmosphere. The lower things are, the more blurry they look, but when they're nice and high, we get to see them more clearly. And so I'm showing you here a sky chart for January 9th, which is sort of nicely into this dark sky moonless period at 7 p.m., so shortly after dusk. And the objects that are crossing the meridian, so objects rise in the east, they're highest when they're in the south, and then they decline in the west. So when they're crossing this green meridian line is when they're at their best, even if they happen to be low in the southern sky. It's the best that we get. So the objects that are the constellations that have objects in them you might want to chase down include Sculptor and Fornax, which are very challenging objects for us in southern Ontario. But then the ones that are higher in this lower air mass range would be Eastern Pisces, Aries, Triangulum, Andromeda, Western Perseus, and Cassiopeia. So those are the kinds of things you want to chase down. 2 hours later, we're starting to see the winter Milky Way heading towards the meridian. So the showpieces embedded within that would be good form. So we have, again, we have the constellation Eridanus coming up here. We have Taurus, Eastern Aries, Perseus, and Camelopardalis. By 11 p.m., we've got the Milky Way right on the meridian, so we're getting those great nebulas and star clusters in Auriga that I showed at the top of the talk. We've got Orion at its best. We've got Gemini and Taurus and so on. And if you stay up really late, you're past 1 a.m. and beyond, you're starting to get into the spring galaxies over here in the Leo and Coma Berenices. By 2 o'clock in the morning, 3, 4 in the morning, these are getting nice and high in the south. So I'll probably wait and view them in a few months, but if you're keen to get galaxies, you can even start now. I often recommend that people who commonly look at the Messier objects to consider other objects that are not on the Messier list. So the Messier list produced by Charles Messier had 110 objects, but they're not meant to be the best of the sky. They're meant to be things that confused he and his fellow comet hunters because they resembled fuzzy faint objects that were sort of comet-like. So I can recommend some non-Messier objects that are fantastic winter showpieces. They include the Rosette Nebula, which is here. if you don't have a very dark sky, you can still look for the bright star cluster in the heart of the nebula. The Rosette is an emission nebula. It's more than a degree across in the sky. It's a fantastic object. You can see it even with binoculars if your sky is dark. And in the Observer's Handbook, Alan Dyer, a RASC member, has produced a recommended list of another 110 objects called the Finest NGC list. And this is object number 32 in that list. Some more, not far from the Rosette, there's an object called Hubble's Variable Nebula. It's a tiny but bright little comet-shaped nebula. I can show it to you in a minute. It's number 33. Then there's the Parka Nebula. I'm proposing that we call this object the Parka Nebula. Some of you will know it as by another name. It's NGC 2392. It's a planetary nebula in Gemini. You can use the averted vision blinking effect on this nebula, but you need a lot of magnification. It's a tiny object. Then one of my favorites for star parties and outreach is the Dragonfly or Owl or ET cluster in Cassiopeia, NGC 457. And then we have NGC 891. It's actually an edge-on spiral galaxy. When galaxies are on their edge, they're brighter in the eyepiece. And so this is a really accessible object for smaller telescopes. It's sitting not far from that star Almanac that I mentioned earlier on. Just let me finish up fast here with a view of some of these objects, just to give you a context of where they are. So here's Orion, here's Monoceros, and here's the Rosette Nebula, the little oops, let me just get this out of here and go back to here. So here's that little tiny comet-shaped Hubble's Variable Nebula I mentioned. You can see that it's not far from the Rosette. And if you keep going in the same direction, you come to a fantastic object called the Christmas Tree Cluster. Here's that planetary nebula I was talking about. It's over here near the waste stars of Gemini. And to finish up, here is the ET cluster, the Owl cluster in Cassiopeia. It sort of sits in the middle of the W of Cassiopeia. And last but not least is this terrific edge-on spiral galaxy. And with that, I think that brings me to an end. Thank you.
All right, thank you, Chris. Very thorough. The sky this month. I typically don't like the moon because it interferes with deep sky observing, but you certainly pointed out a lot of interesting stuff to look at on the moon. Thanks for that. So let's go over to Blake for any questions.
Hi, thanks. We do have a couple of questions. Chris, you Parks in the YouTube chat asked when the lunar X date is, and I didn't recall that date. Do you have it handy?
I can get it for you. Let's see here. The next lunar X that I have listed, let's see. I have one on March 20th.
March 20th?
Early evening.
Okay, thanks.
Yeah.
And I had a question for you on the moon again. Lunar X is sort of one night only, right? But the straight wall is not. Do you have a sense of sort of the latitude? How many sort of hours we can watch it over, or maybe is it more than one night?
Yeah, so it's visible once the moon fills to that phase. It's visible. Let me just get my time up here.
I guess there's kind of a change in the angle of the sun, so you get a long shadow maybe versus a short one.
Yeah, so it doesn't become visible until the terminator gets past it. So after there's first quarter the evening before, a couple of nights after first quarter, now that mare nubium is is being illuminated by shallow sunlight. So after this point, it's visible for a number of nights. It's just going to be most apparent about 2 nights after first quarter, but it'll still be visible for several nights, perhaps slightly less intensely after that.
Right. Okay.
But it doesn't disappear. I mean, it's there.
Right. Good. All right. Thanks a lot. That's all that I see. I'm having a quick look here. That's all I see in the YouTube chat. Thanks.
All right. Thanks again, Chris, for your presentation. Let's move on to our next presenter, and that's Bryon Czarnik. He'll talk to us about football and astronomy, the making of the giant Magellan telescope mirrors. Over to you, Bryon.
Okay, can you hear me? Okay, thanks, Paul. We're entering Super Bowl season. In fact, next week is what some call the Super Bowl of Astronomy, the annual, this time virtual, meeting of the American Astronomical Society. And a few weeks after that is the other Super Bowl, the one to do with football. Now, the people on this image here, the players, they're not in the NFL, but they are players in the University of Arizona Wildcats in Tucson. And these people, they play out of this huge stadium that holds well over 50,000 people. And you'll see on the east side of the stadium there, the Richard F. Karras Mirror Lab. It happened to be the only available space on the campus to put a giant mirror lab. And this lab is responsible for making the world's largest telescope mirrors. The maximum that they think they technically can make these days is 9 to 10 meters across. And the ones for the giant Magellan telescope that I'm talking about, they are 8.4 meters across. Now, a year ago, I was fortunate enough to visit. Most weekdays, they give tours for an hour and a half of the facility. It's a 3-story building with 4 large halls in it. The building itself is separated from the grandstands so that the stamping of feet and roar of the crowd don't upset the delicate operations. And the whole building apparently floats on some giant airbags. There's 4 facilities in this lab. The first one is the furnace area. It's a 40-foot diameter rotating furnace. And the next area is a large 3-story integration hall for working on the mirrors. Next to that is a 28-meter high optical test tower. And of course, the last lab is the polishing and grinding facility. The lab is large enough they can actually work on 3 of the mirrors at one time. And each mirror, each 8.4 meter mirror, takes approximately 4 to 5 years of work to complete. Now, you have here an image of the GMT. It's in the Las Campanas Observatory, not far from the twin Magellan telescopes in the southern Atacama. Work on this began about 2 decades ago. And one of the first orders of business was to make sure that they could successfully make optical quality primary mirrors to the spec required. So that work began 15 years ago. And the entire observatory should be completed by 2029. This map of Chile shows where the major observatories are in Chile, and I've circled where the giant Magellan telescope is. You can see south of there the LSST, now called the Vera Rubin. And to the north, you have the Atacama Array, and what will be another extremely large telescope, strangely enough, called the European ELT. So here are cutouts of the giant Magellan telescope. On the left, you see the inside. The building itself is actually 22 stories tall. That's 63 meters. And if you were to put that building at the base of the Horseshoe Falls, it would stick above those falls by another 15 meters. It's that large. And it's just a massive, massive structure, weighing about 6,200 pounds for the telescope and the pier, which happens to be about half the weight of the Brooklyn Bridge. Yet, even though it's so large, it can rotate 360 degrees in 3 minutes. You can see on the right-hand side that the primary mirror is made up of 7 8.4 meters, 8.4 meter mirrors in a parabolic shape for a total of 25 meters in diameter. The primary is very fast, f.7. They're trying to achieve a resolution of 0.02 arc seconds. You can't see it that well here, but the structure above the primary is holding a secondary mirror. There's 7 of those, and each one is paired with the corresponding primary. They are only 1.05 meters in diameter. The Giant Magellan telescope is 10 times more sensitive than the Hubble Space Telescope and 4 times more so than the James Webb scope. It's like it would be capable of seeing a dime, from the face of the dime, the detail of that, from 100 miles away. So extremely excellent resolution. And paired with something like the JWST, there should be fantastic discoveries in the next few years. Just want to go back a little bit on history, and Chris showed this scope. This is the Mount Palomar Observatory and the Hale telescope. On the left, you can see the 200-inch mirror of the Hale telescope. That's about 5 meters. Now that mirror is made out of Pyrex glass, just like the Pyrex glass in the David Dunlop Observatory in Richmond Hill here in Toronto, which is only 1.88 meters and weighs 2 tons. This particular mirror weighs 20 tons after several tons was ground off it. It's made out of the Pyrex glass, which is borosilicate. And the reason being, they tried to make a very stiff mirror out of fused quartz, but GE wasn't able to scale it up. Turns out that Corning Glassworks in New York was able to do it successfully after a second try. And the mirror was done. It was shipped to California. And after about 13 years, a little bit of interruption because of the war, the telescope was done in 1949. So for 40 years, this was the largest telescope that could be made. It was the king of the scopes. Any larger, there would be problems with gravitational sag, the cost would get enormous, and the time to make the telescope would be excessive. So how do you solve those problems? A professor at University of Arizona came up with a couple of solutions with his colleagues. One of them is to, instead of have just these 36 holes in the Hale telescope, he would make a very comprehensive honeycomb, much as the bees do in nature. It would be very rigid, as a honeycomb is, and the weight would be reduced by 80%, whereas in the Hale telescope, weight was reduced by only 50%. So he made a kiln in his backyard in Tucson and got some custard cups and some Pyrex dishware and melted it to make a sample, and he was successful. However, his wife was not a science experiment in the backyard, so they found space in an abandoned synagogue near the campus and set up the first mirror lab there. Now, the second innovation that he and his team came up with was something called spin casting. So just as in this glass, when you spin the liquid, you get a parabolic shape, which is ideal for mirrors. And you couple that with a mold that is a parabolic shape, and you can save a lot in the cost of the glass and in the time it takes to grind the mirror, because you're already starting with a parabolic shape. So this is what they did. Now, they managed to eventually find that space under the stadium and built a large mirror lab that you saw in the earlier picture. This is an image of the central mirror segment of the GMT with all the people that worked on it sitting around. It's just come out of the oven. You can still see the hexagonal ceramic cores that make the holes in the back of the mirror throughout the structure. The mirror itself takes, as I was saying, 4+ years to make, longer depending on what else is going on. Making the mirror blank is 3 months of effort in the furnace. Then there's the matter of cleaning off the back of the mirror, and I'll show you that shortly, and then polishing the rear surface completely flat and attaching a structure for active optics. And finally, you get to the key part, and that's grinding the front. So a rough grind is done by a large optical generator, and a fine polishing occurs for a process that takes a year or even longer. This cabinet here in the lecture hall shows some of the components in the building of the mirror. The top right shows 3 to 4 kilo blocks of the E6 borosilicate glass that come from O'Hara Corporation in Japan. And in the middle, you see a cutout of the ceramic cores, which are used to make the mold. The ceramic core material is essentially what they use for the space shuttle shield. Each ceramic core is individually sized, it's numbered, and it has a specific position in the mold to create the parabola required for the GMT mirrors. Each core is firmly fastened to the floor of the furnace with those dark silicon carbide bolts. And then the process goes of melting and so on until the mirror is done. I'll talk about the top left there. Those are spreaders that are attached on the back of the flat surface of the mirror, hundreds of those, in order to implement the active optic system. This picture shows you in the top the 1-ton pots, they call them, of borosilicate glass that is made by O'Hara. And what they do with those, they chop them up, they break them up into those chunks of 3 or 4 kilo in size that you see in the lower left. Now, these pots of 1 ton of glass, the university is allotted 1 ton of glass from O'Hara each month. So they have to wait for 20 months in order to get enough glass to make one 8.4 meter mirror. So that's a couple of years added onto the process of making a GMT mirror. This picture shows the furnace area, the casting lab. When I was there, the top showed the furnace blank. The mirror had been made and moved, and it was in the process of waiting for the next activity. But the bottom right shows the mold being set. You see the outer rim of the mirror laid out, and there's the white ceramic cores going around there to provide protection for the edge. You see some of the 1700 ceramic hex cores starting to be laid out in the middle of the mirror, and around the outside rim of the mirror, there are steel bands to hold it all together. Once it's assembled with the ceramic core, the lid is put on, it's heated up and spun around to make sure that everything sets in place properly. And then it's opened up, and the workers get to work to put the glass blocks, 3,500 of them, individually over a course of a week or so on the surface of the hex cores. On the left, you see a fellow with glasses on, and what he's doing, he's checking the rainbow pattern in that block of glass to make sure that it's perfect and doesn't have any flaws in it. Now, this shows the furnace as it was the first time we visited in 2013. The lid has been brought over by a crane and put on over the mirror, and then it's heated up to 1200 degrees centigrade. Now, the melting point of the glass is 1050 centigrade. So once it heats up over the course of a week, the glass melts to the consistency of honey, and it flows over the entire surface, and it flows in between a gap left between each of those 1700 or so hex cores. The spin casting, the turning of the furnace, is at a speed of about 45 miles per hour or 70 kilometers an hour on the outer edge. And the furnace is, when the furnace heats up, that entire 3-story area of the lab heats up to about 90 degrees centigrade. So you can just imagine how hot it is. Now, if you go to the Mirror website, you can see some pictures inside because they have cameras showing it melting and so on and so forth. They have to cool it down very gradually because they want the atomic structure to anneal and the atoms to interlock very tightly. That takes 90 days before the temperature comes down enough that they can open the furnace. Here the furnace is open. You can still see the hex cores in there, and a person's just cleaning that off. Oops. I want to say that the top and the bottom sheets of the mirror are only about 1 inch, maybe 2 inches thick near the edge, near the rim of glass. And in between the hex cores, there's a 1/2 inch gap. So there's 1/2 inch glass ribs connecting the top and bottom sheets. And yet that's still strong enough to withstand wind forces and gravitational forces as the telescope slews through the sky. The next order of business is to lift the mirror with the front surface and put it into a support structure that you see on the right. So the The lifting structure has 36 pads. They're actually bonded to the front with something like bathtub caulking that you would use in your own bathroom. As a matter of fact, to remove those safely once it's in the support structure, an undergrad student suggested they use dental floss, and actually that's what they use to take the bonding adhesive off without harming the surface of the mirror. Here you see the support structures turned on that side, and an elevator structure is brought up behind it so technicians can remove all the carbide bolts. And then using power washers like the ones you buy in Home Depot, they clean out all the residue and they clean out the hex ceramic molds that are in each hole. And once that is done, then they can put plugs, rubber plugs, in each of those individual holes and take it to a grinding facility, and they grind that surface flat, perfectly flat. Once it's perfectly flat and completed on the rear, they can attach those 150 load spreaders that I showed in the earlier picture. And those are the individual actuators that manage the active support system for the large mirrors in the primary. Now, the final stage at the mirror lab is to go through something they called stress lap polishing. This picture was taken when we saw the LSST telescope mirror, the one for the Vera Rubin Observatory, being made, and it was being polished 24/7 at the time. In the back, and I have a close-up to show you, is the 48-inch diameter polisher. Each of those cylinders that you can see move tangentially to the mirror surface and grind off anything that the computer tells them needs to be ground off. This process takes a very long time, as you can see, with decreasing levels of grit until the accuracy of the mirror is down to 25 nanometers. This is a close-up of the large polisher you saw in the earlier picture. Now, during the polishing process, there are frequent checks made in the optical tower. Now, the optical tower, the bottom picture is looking up the tower, and the other picture was the back of segment 5 that was there when I visited a year ago. There's no way of having a crane in there. So to shuttle the mirror and its support structure back and forth, it's actually placed on a number of air carts, and they pump pressurized air in there so that it floats on that cushion. So essentially they're playing air hockey with these giant mirror segments. The test tower has a couple of large instruments in there. One is a laser interferometer you see on the left, and the other is a scanning pentaprism on the right, kind of simulating a star test on the mirror. Now, this image outside the lecture hall was an actual image of one of the mirrors, and it shows how accurate the grinding was. The green means that the surface is within tolerance, within the, this says 10 to 20, but they told us it was 25 nanometers tolerance. And the yellow means that it's still not meeting the tolerance level required. The tolerance level, that 25 nanometers, is like the size of a small virus, 1/5 of the size of the COVID-19 virus, or more practically, maybe 1/1000th the width of a human hair. They also had there a model of one of the 7 secondary mirrors that are used to reflect the primary back down to the instruments. There's 2 kinds of secondary mirror being constructed. One, the FSM, the fast steering one, will have active optics. It's out of a very rigid piece of glass that doesn't bend, doesn't flex. And all the optics do is tip or tilt based on the gravitational forces as the telescope slews through the sky. They may use that for certain observations, and they more likely would use it when it's too windy for the adaptive optics system. So that's the second one. And the mirror there is actually very, very thin, only a couple of millimeters thick. But it has hundreds of magnetically actuated pistons that deform the mirror depending on what the laser stars in the night sky tell it about the atmosphere turbulence and how it needs to be changed. So that would be going on each of the 7 adaptive optics mirrors. Now, when the mirror is completely done and ready to go, it's wrapped in a protective blue shield and then placed in this large container weighing a total of 55 tons. It's transported to a storage location near the Tucson airport, and it stays there until it's ready to be shipped to Chile. One mirror would be shipped at a time, just to protect the investment. Just the labor going into this, which is at the university's cost, no markup, that's about $2 million. Plus, there's about $23 million worth of glass in each 8.4 meter mirror. So it's shipped from Tucson down through Arizona and across Texas through the secondary roads, because the police would not let them go on the main highways. And in some cases, they said the clearance on either side of the mirror would only be 1 inch on the roadway. And it goes right down to Houston and loaded on a cargo ship. And on that cargo ship, it's actually welded to the side of the hull of the ship so that the ocean waves or storms, as it goes down through the ocean, the Panama Canal to Chile, it won't wreck the mirror, it won't get jostled or anything like that. And then it's trucked up the mountain, and then it's time for coat and quench. What I mean by that is each 8.4 meter mirror takes about the equivalent of 2/3 of a can of Coke of aluminum to coat it. So essentially, you could coat the mirror with a 6-pack and still have 1 can of Coke left to quench your thirst after you've done all that hard work. This slide shows, as of a year and a half ago, the mirrors that were cast already, 1 through 5. 1 and 2 are completed. I'm not sure whether 3 is completed yet, because they don't have data for 2019 and 2020, which was kind of slow, a special year. This year, they're going to start up early in the year and cast segment 6. And towards the end of the year, they plan to cast segment 7. It's not yet certain whether they'll do an 8th segment. It's not needed for the telescope, but it was originally planned to have something to swap out the off-axis mirrors so that they could do maintenance on those and minimize the downtime for the telescope. This slide shows you all the mirror castings that were done by the Mirror Lab over the course of the last 15 years. The blue ones being, of course, the giant Magellan telescope mirrors. If you were to visit, and if you can visit after COVID is over, I'd recommend it. It's a very interesting tour, an interesting facility, and lots to see in Arizona as well. I expect they will be working on the remaining mirrors for another 2 or 3 years, almost certainly. So you would be able to see some of that action. First light is planned for 2029. This is the artist's depiction of the GMT, the building there, and then the facility for coating the mirrors, etc., right behind it. And to its left is the small admin building. Off in the distance, you see a road leading to a higher peak. It's not in the artist's shot, but that's where the twin Magellan telescopes, each of those are 8.4 meters and made at this Mirror Lab. That's where they are in Las Campanas. It's possible that they will go live in 2026. I think there's a bit of rivalry with other large telescope manufacturers. They want to be the first. So with 4 mirrors, 3 on the off-axis and the center mirror, all of those will be done. They may go live a few years earlier. And then we'll start to see some interesting results. This shows you here all the major telescope mirrors that exist or are being built around the world. On the top left is the Hale 200-inch that I talked about at the beginning. Down at the bottom left is the James Webb telescope, and beside that, the Hubble telescope. The Magellan telescopes beside that, the giant Magellan telescope, almost the size of a the Raptors basketball court in the bottom right. And the top, above that, on the right side, is the European extremely large telescope, the ELT, and the 30-meter telescope. The ELT will also be in Chile, and the TMT will be on Hawaii. And actually, Canada is a partner in that telescope project. They will be larger than the GMT, but each telescope has its own special purposes, and in conjunction with the James Webb, we'll certainly have some interesting discoveries. Actually, this faint outline here is the previously overwhelmingly large telescope called the OWL that was abandoned by the Europeans. It was 100 meters, and current estimates would have placed the cost around $20 billion to build it. But this class of telescopes that I've been talking about, the GMT, TMT, and ELT, they're all in the billion-dollar class, so more affordable. Well, here we have the 3 telescopes that make up the new class of extremely large telescopes, the Super Bowl of telescopes, if you will, that are 3 times or larger than any current telescope. The ELT, in fact, is larger than the Roman Colosseum on the right, and you can see the GMT and TMT are very similar in size. So we look forward to lots of interesting science from those telescopes. If you're interested, I encourage you to go to the gmtobservatory.org website and check it out. There's an excellent science book that they produced in 2018 that's at the top that has lots of information on the instruments on the bottom right there that they have and the science that they will produce. Very exciting that we'll probably see results that will show whether there are biosignatures in the atmospheres of some exoplanets with these large telescopes. I forgot to mention, but you'll notice that all the telescopes are segmented, but the GMT are very large. So it has an advantage over the ELT and TMT, which have a very complex adaptive optic system. It's much simpler for the GMT. Still complex, and the most complex ever built so far, but more manageable. Plus, they have the largest possible telescope surface with a guaranteed curvature on the wave surface. So that's a definite advantage for the GMT. That's it. Thank you very much. And if there are questions, Blake, I'll be happy to take them.
Thank you very much, Bryon. That's certainly an engineering marvel. Amazing stuff. Let's go over to Blake. Any questions?
Yeah, thanks. Leo2 CAF asked the question regarding cooling and cracking. Let me find the question here. Back at the time of the casting of the large Pyrex mirrors like the DDO and the Palomar, cracking while they cooled was a problem. So he's asking, have the new materials and techniques overcome this? And I'm curious how.
It seems to have overcome it. With the Hale telescope, the mirror there, the first time it failed because one of the molds came loose and floated to the top. So actually that mirror is on display in the museum, and I've seen it there. If you want to go, you can see it there. What almost destroyed the final successful mirror was a once-in-a-century flood of the river below the factory that they had to sandbag and protect the mirror, which was in its cooling phase, and it would certainly have cracked if the water had reached it from the river. So as far as I know, they haven't had failures with the process they've been using at the University of Arizona.
Yeah, I guess with these bigger projects, they don't want failures.
Yeah, it's an advantage with the ELT and the TMT. The mirrors are all smaller, more manageable segments, but the trade-off is, of course, the computer control and adaptive optics are incredibly complex.
Mm-hmm. You had mentioned that the provider of the glass could only do so in like certain quantities. There was an allotment or some sort of restriction.
Right.
Why was that?
I don't know. It could be that the demand for optical quality glass was so great that they couldn't meet all the requirements, and they divvied it up between different universities and different companies that were requesting it. That's my guess as to what happened. I mean, a ton of glass is an awful lot.
Yeah.
I think some refractors use this kind of glass, and they're not using anywhere near a ton. That would make a lot of amateur astronomer refractors, that's for sure.
Very good. I have one more question from me, and that is, how much are these tours that you've been taking? Do you recall the prices?
I think they're maybe $15, and they're a nominal sum. The tour groups are limited, maybe 15. I'm not sure we had 20 people, but they were limited in size because of the close confines and the walkways that you went through. And they didn't want everyone going through there.
And how far in advance did you have to book? You obviously planned some trips around it.
Well, it depends. February is winter season, which is busy down there. I booked a few days in advance and was able to get on a tour.
Great. Okay, thanks a lot, Bryon.
Okay. Cute.
All right, thanks again, Bryon. Let's move on to our next speaker, and that's Tom Otvos. And he'll give us an update on making a thin meniscus mirror telescope. Over to you, Tom.
Thank you. So I would like to talk about Artemis, which is the name of my telescope. And this talk is kind of an update to a talk or a presentation that I gave about 2 years ago that discussed in detail about making thin meniscus mirrors. And so I'm going to recap a little bit of that, but if you're interested in more of the details about how the mirror actually is fabricated, I suggest you look up in the YouTube archives for that talk. But otherwise, I'm just going to quickly recap that and then go on to detail the final construction of the telescope and observing reports and that kind of thing. So first up, the Artemis is basically a thin meniscus mirror telescope. And for those of you that don't know, a meniscus is basically like a contact lens. It's a thin, curved piece of glass. It's curved on the front and back, and generally, although not necessarily, it's of uniform thickness. And you might be wondering, why would you want a meniscus for a telescope mirror? And the primary reason is it's a dramatic weight savings. If you look at the image on the top right there, that's a 25-inch mirror that's using what would be sort of a typical thickness for a telescope mirror, which would be 2 inches. And that amounts to 981 cubic inches of glass, or roughly 100 pounds. The image below that is another 25-inch mirror. This one is a half-inch thick meniscus mirror. So the total amount of glass ends up weighing about 20 pounds. So for the same aperture, you're looking at a fifth of the weight of the glass. And when you have a thinner mirror, basically that means that you get a lighter telescope overall for a given aperture. And the other benefit of having a less amount of glass mass is that the glass itself cools much more quickly, so that when you get it out into in the evening, you don't have to wait a long time for it to acclimatize to the temperature. So that's typically why you would use a meniscus for a telescope mirror. Now, the other thing about Artemis is that it's a fast mirror. It's got a focal ratio of f2.6. And so you might be wondering, why would you want to make a mirror so fast? Basically, focal ratio impacts a number of aspects of the telescope design, but frankly, the main motivation for me was portability. Basically, I wanted a large aperture telescope, but I didn't want to have a really, really massive scope that I could haul, to observing sites. Basically, if you have a big aperture and a big f ratio, you're ending up with a very long telescope that needs at least step-up access or ladder access. Conversely, big aperture and small focal ratio means that you can have a large aperture telescope that can easily fit into the trunk of your car without a lot of massive disassembly. Another benefit of fast mirrors is that you typically have a much larger field of view. So you trade off by having less magnification, but you end up with a larger field of view, which makes it a very pleasing telescope to use for viewing extended objects. And we can talk a little, and I'll talk a little bit more about that later. So As I talk about in my previous presentation, basically kilns are the enabling technology for making meniscus mirrors. And what you do is you put a piece of glass into a kiln onto a shaped form, and then using a proportional integral derivative controller, or a PID, it's basically a microcontroller for the kiln temperature. And what that enables you to do is very precisely ramp up the temperature to the point where the glass starts to melt. Not the same temperature that the GMT was, where you're actually making it flow, but you just want it to be pliable. And then gravity takes over, and basically the glass slumps over the form. And then you again use the temperature controller to very gradually decrease the temperature to allow the glass to anneal, just like they're doing for the in the mirror lab that we just heard about. Although in my case, I'm not letting it ramp down for 30 days. It's typically about 2 days. But the idea is the same. You want to very slowly cool the glass down so that it anneals properly and you don't bake in any stress into the glass. The PID is a relatively inexpensive thing, and that coupled with a cheap ceramic kiln allows you to actually slump glass. So all of this I discussed in detail in my first talk. And when we last left the story, the glass that I had originally created, it was very close to being finished, and I was doing star testing, and the glass tipped out of the star test rig, fell on the ground, and broke into two. That was very unfortunate. It took about 18 months to get to that point. And after about a month of mental recovery to sort of figure out what I wanted to do, basically I got back on the horse and slumped a new piece of glass. And I was able to, within 5 months, get back to where I was in the first 18-month odyssey. So definitely I learned a lot along the way, obviously, and that allowed me to fairly rapidly get back to where I was. So, and that was roughly, when I presented last time. So the bulk of 2018, once the glass was slumped and figured, the bulk of 2018 was spent testing the glass, testing the figure, doing star testing. Initially, when you're figuring these mirrors, you use bench tests like Foucault for traditional telescope mirrors. But for mirrors that are faster, the Ronchi test is typically used. Some people are using bath interferometry, which is a kind of a laser interferometer, again, kind of like the testing that they're doing for the GMT telescope. But basically, through a bunch of star testing, I was trying to, get to the point where I could call my mirror done. Now, the thing about the testing was that it was good, but it wasn't great, and it was hard to isolate exactly why the mirror wasn't giving really, really great star test results. And one of the potential culprits was collimation. When you're talking about mirrors that are f2.6, collimation becomes a very, very finicky thing. So you need to have really, really precise collimation. And so it came to the point where the test rig that I had, which is shown in this image here, was a quick and dirty one that it didn't seem like it had the chops to allow me to really decide that the mirror was done. And so really the only way to be sure that the mirror was done was to actually build the telescope into which it was going to be placed, so that I knew that that all of the tube assembly that was holding the mirror was rigid, and I could very unequivocally assess the quality of the mirror. Since I had to build the OTA eventually, I decided that I would actually build the OTA before I made the final determination of the mirror's doneness. And so using Mel Bartel's zip Dob as the model, which was the inspiration for this telescope. And if you haven't seen it, it's just like a really, really cool looking telescope that actually doesn't look dissimilar to the telescope that's on the screen right now. I used his model as a starting point and modeled it in SketchUp. and but redid all of the geometry to match the optics that I had for my particular telescope. Now, and so I ended up with the design that you see on the screen. One of the things, unfortunately, that dropped out of the design that really attracted me to ZipDob in the first place was in his design, it folds up like a clamshell, which was really, really cool. I loved watching it fold up, and I thought that would be really, really nice from a portability standpoint. Unfortunately, in my case, because I'm that much shorter in terms of focal length, his was an f3 and mine's 2.6, just the geometry just didn't work properly for allowing any kind of folding that made it worth putting in the mechanical design of folding. I wasn't getting the compactness bang for the buck. So I decided to simplify the design, and so it became a rigid OTA. So lots of iterations, and with Mel's generous help, I got the design together, and then I started to fabricate it. My kitchen basically became the staging area for large glue ups, and over the next several months, really stretching my woodworking skills and curve cutting. All of these curves are cut by hand using a jigsaw, including the circles. I basically spent the next several months cutting the parts and gluing it up and putting it together, and ultimately ended up with this. So this is Artemis, or this is the OTA for Artemis, and you can, if you're seeing my video, you can actually, it's over my left shoulder, but this became the design that I ended up doing. So let me just point out a couple of interesting things about the design that kind of make it unique. First, there's just this general merging of function and form where, yep. So with the SketchUp model in hand, I started to build the optical tube assembly. The work spanned a couple of months and really stretched my woodworking skills, especially cutting up the various curves, including the circles, which I did all by hand and a jigsaw. And used my kitchen as a staging area for gluing up the large pieces. But basically over several months, it kept hacking away at it until I ended up with this. So this is Artemis, or the optical tube assembly for Artemis. And let me just sort of highlight a couple of key design elements that make this somewhat of a unique telescope. First, there's just this merging of function and form, where the structure also, like the structural J-arms, also serve as altitude bearings. So this is really only possible because of the compactness of the telescope that's afforded by the really fast primary. In the mirror cell itself, it's just a very, very simple but very effective 9-point mirror support. Again, because the mirror is very, very lightweight, we don't need super elaborate supports. The collimation is done through screws from behind. So basically there are 3 screws that control the 3 triangles that each have 3 support pads on them. And the screws move in and out and they achieve the tip and tilt of the mirror for collimation. The diagram here just shows a bolt, but they're now actually Allen key hex bolts, which are a little bit easier to manage. But it's still I still find the collimation a bit unwieldy. The mirror is supported on a 2.8 support that's 90 degrees apart, and the mirror rides on Teflon, which is fairly effective, although I think I'm going to revisit that and actually put roller bearings on the points of contact between the mirror and the support. And I'll also note that some meniscus mirrors that I'm working with, they're now considering coring out the center part of their mirror, and that's ordinarily hidden by the secondary. It's in the secondary shadow, and then supporting the mirror from the center so that you don't have this 2-point support at the bottom, which can help when your mirror gets very large. This is only 14 inches, but people that I'm working with, they've made 25, 30 inch mirrors, and the meniscuses can get a little bit floppy. And so consequently supporting it from the center is one way to work around that. Another interesting aspect of this design is a wire spider. And it's a very, very simple and shockingly effective way of supporting the secondary mirror. 22 gauge wire holds the hub, to which the secondary mirror is attached. And the wire doesn't have to be particularly taut. It's just all through the geometry of the crossing wires that make it incredibly stiff. And because it's 22 gauge wire, the diffraction spikes are very, very small. There are screws that are in the ring of the upper tube assembly, and those screws basically just tighten and loosen the wires a little bit, and that's how you achieve the pointing of your secondary. I'm actually going to be redesigning that part as well, because I've recently jumped into 3D printing, and so I'd like to redo that wooden hub piece that's holding the mirror and 3D print it to make it a little bit more stiff, as well as reduce some of the weight. On the altitude and azimuth side of things, there's a very low profile flex rocker that basically rides on Teflon bearings, which rides on the Formica ground ring. And there's also Teflon bearings on each of the 4 corners of the flex rocker, which then ride on Teflon strips that are glued to the J-arms of the OTA. I've got skateboard bearings that are basically on the corners of the flex rocker to basically keep it positioned on the ring. But aside from that, it's a very, very simple and lightweight support. The ground ring itself goes on this very, very simple tripod that is stupidly simple and actually really ugly. But I did it as a very quick and dirty base that I needed because I wanted to get the telescope up to Starfest in 2019, and I hadn't created a proper base for it yet. So I did this, and unfortunately it was so effective that I haven't really changed it yet. I would like to make it out of nicer wood at least, but essentially the Y shape, you can see there's like, there's the hook that basically is keeping it in the Y shape, but when you unhook the hook, there are hinges, and basically the three legs fold flat against each other. So you can put the whole thing in your car, and I can fit all of the ground ring and the flex rocker and the and this base into my trunk, as well as all my eyepieces and everything. And I can put the Artemis tube on my back seat of my BMW, and I'm good to go. And what's really cool is that basically the total setup time in the field for everything is about 5 minutes. Which is a real nice nice thing, because here in Mississauga, I mean, I have to drive anywhere where there's a dark site, so being able to quickly set it up is definitely a plus. This is Artemis next to my old telescope, which was a typical classic f7 8-inch Dob. Aside from the photo op here, the main reason that the two scopes are side by side is I was doing some more detailed testing of double star resolution to really shake out the optics on Artemis. So that's why that's there. Now, aside from the mirror and the OTA, another thing I wanted to touch on with Artemis is the coating. And the mirror on Artemis is actually silvered. And the reason for that is quite simple. Inherently, silver is more reflective than aluminum. And these curves here demonstrate the relative reflectance of them. When you have enhanced aluminum coatings, they're pretty much like silver. But if you've ever paid for enhanced aluminum coatings, especially on large aperture mirrors, that can get very, very expensive. So one of the things that I wanted to explore with Artemis was actually coating the mirror with silver. Now, the question with coating mirrors with silver is, how do you do it cheaply using just basic chemistry? Because obviously in the old days, that's the way they did it. They silvered their mirrors, and it's only during the middle of the 20th century, up until current times, that aluminum has been the thing. But previous to that, it had been silver. And so the question is, can you do something like that at home cheaply? And the answer is unequivocally yes. There's a company called Angel Gilding that basically provides silvering kits that are originally they're silvering for creating decorative mirrors. But we came across this and we thought, well, hey, wouldn't this be interesting to use on a telescope mirror? And they sell a spray silver kit, all of the parts that you can see here, which includes the chemicals as well as the spray bottles and spray pumps and everything that you need to do your silvering. And they have enough material there to coat 24 square meters of surface area, which is a lot of glass. So, and all of that's for about $400 to get all of the parts. And the chemicals themselves just to do a mirror is well under $20. So you can pay to have your mirror professionally alumnized for hundreds of dollars, or you can do it for $20 at home. Now, if you follow the process and the main thing about the process is cleaning. You have to be ridiculously slavish about cleaning your mirror surface. The silvering really, really works. And the link on the slide here basically describes in detail the silvering process that I and a number of people that I work with are successfully using, and with very great results. So here is my silvered mirror, and I call it beginner's luck because, you know, I managed to get a really, really good coating the first time. But the really cool thing about this is that because it's so cheap, if you make a mistake or your mirror isn't clean enough, they also include chemistry to wipe off the silver. And if you've never seen that done, I actually have a YouTube video of it because it is just so cool that you just spread this chemical onto the silver and wipe it, and you're essentially just erasing the silver, and it looks really, really cool. Anyhow, but the point is that if you make a mistake, you can very easily resilver your mirror, and just basically keep doing it until you get it right. And there is a bit of a learning curve, but once you've done it a few times, it's actually fairly easy to get a really, really good quality silver coating. Now, the problem with silver is tarnish. So that raises two questions. The first is, how can you extend the life of a silver coating so that you can have the silver last for ideally at least one season? And then the second is, how do you really know when it is time to resilver? So to answer the second question first, some people that I work with had developed this thing that we call the PMRT, the Poor Man's Reflectivity Test. And basically the idea is you measure a white object, in this case a piece of Teflon, and you take a photograph of it, and you break it up into the three different color channels, and you measure the source material, which would be above the mirror, with the reflection. And if you look really closely, you can see that the reflection of the Teflon is slightly yellowed. And that's an indication, you know, of the fact that this mirror is getting close to needing to be silvered. But basically what you can do is you can measure the relative colors in the red, blue, and green of the source and the reflection, and infer from that the reflectivity in each of those color channels. And the person that devised this test actually had access to really accurate lab equipment. And the chart that you see here basically shows that the Poor Man's Reflectivity Test gives a pretty reasonable, like within 1% or so of the actual measured reflectivity using a spectroradiometer. So this gives us a tool to allow us to measure the reflectivity with a reasonable amount of accuracy. But the point isn't to get an absolute value of reflectivity, although it's nice to know. What you want to do is have a repeatable test that you can, you know, do every couple of months. And when your reflectivity drops by by an arbitrary percentage, then you can say, okay, well, now it's time to silver my mirror. Now, the other aspect is how to protect the silver from tarnishing. And another person had discovered this product called Midas Tarnish Shield, which is basically a product for jewelry makers. And what it does is it atomically bonds to the silver and provides really extensive protection against tarnish. And what they ended up doing was doing some really aggressive accelerated life testing of microscope slides that they had silvered. And they basically dipped half the slide in tarnish shield and then put it in this really toxic environment. And you can see on the left-hand side of the slide how badly tarnished the silver got. And on the right-hand side, it basically looks brand new. And so a number of us now have been using Midas Tarnish Shield to protect the silver and have gotten multiple seasons out of the silver. One person, in fact, he's got a 28-inch mirror, and it's been 2.5 years now since he's silvered it, and it's still going strong. So, and it's important to point out that this is at the atomic level that this is happening, and so it's not like we're painting on a coating on top of the silver. So we're actually changing the chemistry. And the same person that was doing the spectroradiometer tests for the PMRT also did tests to make sure that the Midas wasn't actually changing the optics at all. So we're not painting on something, we're basically changing the chemistry. Now, unfortunately, in practice, it turns out that tarnish isn't the only enemy of silver, and humidity also plays a factor, as well as dust. And so you can't just dip your mirror in Midas and expect your mirror to be perfect for years and years and years. You do need to take extra steps to keep the humidity low when you're not using the mirror, and also keep it covered to keep the dust off. And we're also still looking at other products that we can use in combination with Tarnish Shield to provide some mechanical protection as well. But we haven't really found anything great yet. So right now, the best thing to do is to just protect your mirror. The other cool thing is that Angel Gilding, the source of the silvering product, has been following what we've been doing, and we've been keeping them in the loop. And they are now also selling the Midas Tarnish Shield as an Angel product. And the benefit of that is cost, because right now, if you were to buy Midas from the source, it's like a big, huge jug, and it costs like $60. And that's assuming you can get it across the border, whereas the Angel people are selling, smaller, just several ounce bottles of it, because you really don't need an awful lot of this, and for a much more affordable cost. So that's really cool too. So having done all of that, does it pass the test? Well, the first public viewing of Artemis was at Starfest in August of 2019. And then a month later, I took it to the Black Forest Star Party in Pennsylvania. And I have to say, it was definitely a head turner. And, and when I had it set up in front of my tent, people would walk by and they would go like, what the heck is that? And they would ask to, and I would give them, some people were very interested in the whole fabrication of it, gave lots of talks on it, and lots of people came back at night to look through it. And I have to say, it was really it was a joy to use at a dark sky site. Wide field views of the Andromeda Galaxy, Veil Nebula were excellent, and where you could see like large parts of the Andromeda Galaxy in your field of view, or the entire East Veil or the entire West Veil all in one view. And more gratifyingly, at the Black Forest Star Party, I got to meet Mel Bartels. Sorry, I had met him before, but he actually came out because he was giving a talk, and because he was traveling across the country, because he lives in Oregon, he didn't have a telescope. So basically, he spent the entire evening observing with me, and he was really, really impressed with the optical quality, which was just like such a huge relief, because he's a master optician, and to get his kind of blessing on the optics was really, really satisfying. So after that, spent fall and winter on my own personal Messier project, and for the most part, I was really, really happy with the way the telescope was performing. However, being an ATMer, I'm never quite done. And one of the things that bothered me about the performance of the primary in Artemis was that high-powered views were soft, and so on very high magnifications on the planets, which is tough to do on an f2.6 anyhow, or observing close doubles. I had difficulty splitting close doubles, and it was, the more I used it, the more bothered I got by it. And while that's not necessarily the primary use of a wide field scope like this, it still was enough to bug me. And and so I ended up doing a bunch of tests because it still wasn't clear. Was it a collimation thing? Was it an eyepiece thing? Because I'd been using Explore Scientific eyepieces, and Mel's a huge Teleview fan, and so he was saying, well, you should get an Ethos or an Eigler or whatever, as well as comparing it to my other Dobsonian. Eventually, I eliminated all the other options, and the likely culprit turned out to be surface roughness. And here's the Ronchi image for the final optic. And while it is a good match for what it should be, the lines aren't as clean as they should be. And after trying all of the other things, we decided that it was probably surface roughness that was just kind of softening things up and screwing up the high power resolution. So when it came time for me to actually need to re-silver Artemis, I took that opportunity to touch it up and try and improve the view. Unfortunately, the touch-up touched it up a little bit too much and kind of messed up the figure. And so as a result, Artemis is currently offline because it's currently being refigured, which is kind of nice too, because it allows me to kind of go take a step back and really spend some time getting the smoothness down and putting another high quality figure in it that will hopefully yield better performance. But right now, Artemis is offline, and hopefully soon that'll be I'll be completing that in the next month or two. I've been working on it over the Christmas break, so hopefully in the next couple of months it'll be back online. And then once I do that, then the other major things that I want to add to it are an equatorial platform to give me some degree of tracking. And then what I really want to do is start to get into EAA, because I think that the combination of the wide field views with sort of near real-time stacking, I think that would be a great tool for outreach, because I really do want to use this for outreach in my neighborhood. In particular, we've got lots of kids here, and just to start getting budding young astronomers interested in the sky. So that is basically Artemis, and I'm happy to take any questions that anyone might have.
That was absolutely amazing. A great accomplishment in so many ways. Well done.
Thank you.
That wraps up the speakers for this evening. But first, questions for Tom.
Okay. I'll just do a couple of questions here so we can move on quickly. Bryon asked, how do you get an even coating of the silver on the mirror, and how do you know that it's done the right way or applied the right way?
It's yeah, and it's basically chemistry is what it is. That's the quick answer to it. You're not actually painting the silver on. You're using chemistry to bond the silver to the glass, and so it's a two-step process. After you clean the glass, you do a process called sensitizing, which basically you spread stannous chloride, I think it is, a tin essentially onto the surface, and the tin basically bonds to the glass, and then you wash off whatever residue you've got left, so that there's basically tin on top of the glass, and then you use your silver compound to basically bond to the tin. So the silver bonds to the tin bonds to the glass, and it's all done at the atomic level. So you're not painting silver on, so there isn't a thickness thing. You just need to make sure that your entire surface is covered. And the quickest way to test that is to just hold it up to a bright light. If you have just like a very thin coating of silver, so you don't have a full bond yet, then you'll be able to see through your mirror from behind. and as long as you can't see through your mirror, or you'll actually see just like a very fuzzy light, and that way you can sort of that way you know that you have an even coating, first of all, because if you have patchy brighter spots and less bright spots, then you know that you haven't got a completely even coat. And then you just spray on a little bit more and hold it up to the light until you're satisfied.
Okay, very good. Ari asked if you have done any photography with your scope at this stage.
Not yet, no. It was purely visual when I was using it, and that's one of the reasons why I want to get into EAA, because at that speed, it's not going to take a lot of seconds to get some pretty deep images, and and so I'm very excited to try and get to the point where I can take even just like a couple of minutes, which is why I want to get the equatorial platform going as well, because I don't need a lot of tracking. I just need enough to get a couple of minutes of accumulation, and I think that's gonna yield some pretty cool results.
Yeah, that's the spirit of Hyperstar and FastStar on SCT telescopes. They turn them into F2 instruments. Yeah.
Mm-hmm.
And maybe if you can answer quickly here, what's next after Artemis?
That's a really good question, and I've been debating whether to go bigger or to go smaller. One of the things, and this is along the lines of EAA, there are a couple of new telescopes out there that are just totally digital, right? The what's it called? The French one.
Oh yeah, the Unistellar.
Yeah, yes, exactly. And I look at that, and while it's an interesting and cool product, it's really not bringing tons to the table that can't be done with off-the-shelf stuff. And so I'm sorely tempted to try and do one of those, maybe in a 6-inch version, because if I can do a 14-inch, I can certainly slump and figure a 6-inch fast scope. So I think it would be really cool to do that. But then, there's always bigger too. So I don't know. Mel Bartels, when I was doing Artemis, he was at that time doing a 25, and you saw his 25 on my first slide there. Since that time, he's moved on to a 30. So right now he's actually figuring 30 inches, and he's actually got 2 of them that he's doing concurrently. And so he's figuring them both at exactly the same time, and they're getting pretty much exactly the same figure, because originally he wanted to do a binoscope, but now he's thinking he's not going to do a binoscope. But anyhow, so he's doing a 30-inch, and then after that he's doing a 42. So I'm kind of, I'm envious of those large apertures as well. I mean, it would be fun to have a meter telescope, but that would be a big job too. So,
right,
and I'd need a bigger kiln.
And a bigger kitchen.
Yeah, bigger kitchen too. Yeah.
All right, thanks a lot, Tom. Good to see you again.
Any other questions? Feel free to email me, and I'll be happy to field any other questions.
Very good, thanks.
Thank you.
Great, thanks again, Tom. Let's wrap up the evening with announcements from our president, Tom Luton. Go ahead, Tom.
Thanks, Paul. Hi, everybody. Hope you had yourselves a good holiday. So let's get right into the announcements. So as Paul said earlier, we've got 2 types of meetings here. We've got our recreational astronomy nights, and we have our speakers nights. They're available live. They're also available recorded. If you happen to be here for the live chat, please use the chat, say hello, enter some questions for the presenters. If you're a new member, introduce yourself, and if you've come from far away, let us know where you've come from. Our next meeting is on the 20th in 2 weeks. Professor Nassim Bazorgnia, I'm sorry, I've mangled that horribly, searching for the mysterious dark matter, right here on YouTube. Our recreational astronomy night is going to be on the 3rd of February. Arnold Brody, we doing the sky this month. Artash and Arushi Nath will be talking about do-it-yourself asteroid astrometry using Python. An awful lot of syllables in that one. And Blake Nancaro will be talking about weather forecasting resources for amateur astronomers. And if you'd like to present yourself, please drop a line to our own Paul Markov. Now, COVID-19 has put an awful lot of our work on hold, but we are planning virtual star parties and EPO talks with the Ontario Science Centre, with Millennium Square, with the David Dunlap Observatory, with the St. Clair and O'Connor community, with the Dunlap Institute, with Brownies, Cubs, Scouts, schools, etc., and through our course, New Observers to Visual Astronomy, NOVA. So keep an ear out for that, and contact public education at rascto.ca for more info. Our observing sessions are also suspended due to COVID. Our sessions would be at Baby Village Park, at the Long Sault Conservation Area, or right at the Science Center. Again, because of COVID, the Carr Astronomical Observatory is closed to maintenance personnel only. Also, winter has set in, and the road is closed due to snow. So you'd be snowshoeing or tobogganing in anyway, but it would, in a normal year, things would be open for winter use. Sorry to say. Now, we still have need for volunteers, even with things sort of partly shut down. So if you are a RASC Toronto Centre member and you're interested in helping and you've got some free time on your hands, please drop a line to the volunteer coordination team at volunteer@rascto.ca. We've got a job open. We're looking for a new head of our light pollution abatement committee. So if you're looking for something to do on a casual level and you care about the environment, let us know. One really cool thing about this job is it comes with the best job title, Prince or Princess of Darkness. Again, volunteer@rascto.ca. So our very popular stellarium training courses continue to fill up, I'm sorry to say. The level 2 course that's going to be at the end of January is full, as are the level 1 courses at the end of February and the beginning of March. More courses, though, are planned, more sessions, as well as a level 3 and stellarium for educators. Full details at the link. And this is where I plug membership for the RASC. If you're looking to join for the first time or looking to renew, you can do so online at secure.rasc.ca. One note is that currently the system is going through a transition. We're bringing new software online within a couple of weeks, so you might wish to delay just a little longer. COVID-19 has thrown a lot of things out of whack. Some folks are finding themselves in a bit of a financial problems these days. If so, and if you still want to join the society, the RASC does have an emergency fund. It is completely confidential. Speak to Adela at the national office, mempub@rasc.ca. We've also got a number of items for sale at the national office's e-store, the Observer's Handbook, and as well the Observer's Calendar. Normally this calendar would be available at meetings, but since we're not meeting in person, you'll have to order your calendar this year through the e-store. And that brings us to the end of the meeting. Everyone, I'd like to wish you have a good night. Thank you very much for joining us. Please follow us on social media. Please like and subscribe and click the notification bell for further YouTube videos. And on behalf of the center, be safe and keep looking up. Good night.